Hi, it's Mr. Baker here with another physics video. Today we're going to be looking at lenses. Okay, so today we're going to be looking at lenses and magnification. So what's the difference between these words? So what do these words mean and what's the difference? So what I'd like you to do is just to pause it, see if you can write down what you think these words mean and what the difference between these words are, and then I'll show you what these mean. Okay, so pause it there. Okay, so I'm going to go through it, so hopefully you've paused it and you've had a go. So we've looked at what the terms virtual and real are before, so let's see if you can remember that. So a real image is one that can be projected onto a screen, and a virtual image is formed where the rays appear to come from. So for example, like behind a mirror. An upright image is one that is upright, and an inverted image is one that is upside down. A magnified image is larger than the object, and a diminished image is smaller than the object. So let's have a look at lenses. Okay, so lenses are used to form images by refracting light. A convex lens will bring parallel rays of light to a focus at a point called the principal focus. The distance from the lens to the principal focus is called the focal length, and that's measured in meters. You can see we've got three parallel rays of light. They're being refracted by the biconvex lens. Bi means two, convex is this shape. So we've got this shape on both sides of the lens, and that's why it's called a biconvex lens. You could just have a convex lens which only have the shape on one side of it. You've got the focal length there that's going from the middle of the lens to the point of the principal focus, the focal point. So parallel rays of light are as if the light was coming from infinity, and then we've got this imaginary line passing straight through the centre, which is called the principal axis. To find the focal length of a concave lens, rays parallel to the principal axis must be directed through it. As the rays diverge, we trace their path backwards to find the point where they cross over. This is the focal point, while the distance from the focal point to the centre of the lens is the focal length. So to work out the magnification of a lens, what we do is we look at the image height and the object height and we compare them. So it's the image height divided by the object height. And that's actually the same as the image distance divided by the object distance. And we're going to look at a little practical where you can see this in action. So you might use things like this in a practical looking at images and objects when you're looking through a lens. So you might have a ray box with a crosshair, which would be the object. That would get projected through a lens and then it would be focused onto a screen. And then you might take some distances, the distance from the object to the lens and the distance from the image to the lens. You could also measure the object height and the image height. And then you might want to fill in a table that looks like this, which compares the distance from the lens and the height of the object, and the same for the image. Alright, here's a little online investigation that you could do. You can see that we've got a converging lens here. On this side we've got the object. So this is the thing, the light is coming here and it's reflecting off this object. And then over here, this is where the image would form. So if we had a screen or something on this side, then we'd be able to see an image on that screen because of the light reflecting off the object, going through the lens, focusing at a point, and we would see an image. And so you can see here, this arrow, instead of physicists being amazing artists, we tend to draw diagrams. And so this is a diagram of the object, which just is drawn as an arrow. So the arrow shows you the height. So it's a scale drawing of the height of the object. And it's also showing you which direction it is. Is it upright or is it upside down, which we call inverted? Okay. So that's the things to look at. And so what you can do is you can change the distance. So the object distance is the distance from the object to the lens, and the object height is the height of the object, so that's not going to change. The actual height of the object is not going to change. And then we can have a look at what happens to the image distance, so how far away is the image from the lens, and how far away is the how big is the image as well. Okay, so let's have a look. So we can change the object distance, so it's gone from 200 to 180, and then we can see what would happen to something like the image height. So we could do an experiment to say, how does the object distance, how does the distance from the object to the lens affect the height of the image. Now it says minus 7.69, and it says minus because actually it's not pointing up, it's pointing down. So it's an inverted image, and this is what happens with converging lenses. So as the light comes in, the image that's formed is upside down. So if we went back to the beginning, our object distance was 200, our image height was minus 6.67. If we go to 180, if you can do it, the image height is minus 7.69. If we go to, let's go crazy, let's go to 100, the image height is minus 20. And now you can actually start to see this image. It looks like an arrow. It is an arrow. It's just pointing in the opposite direction, and it's showing us the height there. And then we could change the distance a little bit more. We could get it closer, and we could see how that affects the image height. So you can do this experiment by going to this website, which is physics.bu.edu, and then lenses. And doing an experiment like this shows us the relationship between the object distance and the image distance, and the object height and the image height. And what we find out is that the object height divided by the object distance equals the image height divided by the image distance. So let's have a look at a summary of what we've done then. So lenses work by changing the direction of light because of refraction. Converging lenses make parallel rays converge to a focus. The point where the rays focus to is called the principal focus of the lens. A diverging lens makes parallel rays diverge or spread out. The point where the rays appear to come from is called the principal focus of the lens. The distance from the centre of the lens to the principal focus is called the focal length. Okay, so that's the end of this one. This is what you should be able to do. You should be able to distinguish whether a lens is converging or diverging based on a simple ray diagram. You should be able to state the difference between real and virtual images and investigate the image forming properties of a converging lens. And you should be able to explain ray paths through a lens in terms of refraction and the focal point, and how to calculate the magnification of a lens. Okay, so that's been another physics video. I've been Mr. Baker, and I'll see you next time. Thanks very much.